Again, hi, welcome to Mathematics 200, again, MAT 200 Business Calculus. Today, our main topic will be derivative of log functions. Again, derivatives of log functions. And that's our main objective today. So to find a derivative of log functions, first we shall go through what is a log function, and then we start the derivative. So example here is that if we have a function y equal to log base ax, this is again a log function. A should be a value that is greater than 0 and also not equal to 1. So for a greater than 0 and a not equal to 1, the log function will be y equal to log base ax. Again, x will be a domain that is greater than 0, and the base is a, and this we can transform a log function to exponential function. So as we said, y equal to log base ax, the exponential function will be the base a raised to the power y equal to x. So exponential function of a raised to the power y equal to x is the same as y equal to log base ax. The a again is called the base in both the log function and also the exponential function. So this is a log function, and normally the graph always is increasing. Now we want to go to what is derivative of y equal to natural log x. Now y equal to natural log x, graph will be in this form, increasing, and y can never be a negative value, so we can see that the y will be very close to 0 beginning. And this is also an example. So here we said if y equal to natural log x, then the law of derivatives said dy dx will give you 1 over x. So in short, derivative of y equal to natural log x is the same as 1 over x. Now if we are doing the chain rule, then dy dx equal to 1 over u, then derivative of u, which is the u dx. So that's the formula again, finding the derivative of y equal to natural log x will always be 1 over x. Dy dx will be 1 over x. Also the chain, if we have a composite function, then the chain will also apply. So we have 3 examples here. Hopefully this may help us. Let's go through the first example. We have f at x equal to natural log. A natural log means the base is e. The base is e, natural log. So here we have a natural log x raised to the power 4 minus 3x plus 7. So again, the answer of this will be, we said the natural log x, the derivative of natural log x is 1 over x. So here we get 1 over x to the power 4 minus 3x plus 7. Then the derivative of, multiplied by the derivative of x to the power 4 minus 3x plus 7. So we are using the chain rule here. So again, the derivative of f at x will be 1 over x to the power 4 minus 3x plus 7, multiplied by the derivative of x to the power 4 minus 3x plus 7, which will give us 4x cubed minus 3x plus 0. We know the derivative of a constant value is 0. So our final answer will be 4x cubed minus 3 over x to the power 4 minus 3x plus 7. Again, here the chain rule apply. So 1 over x to the power 4 minus 3x plus 7. Then derivative of x to the power 4 minus 3x plus 7. Now let's look at the second one. So the second one, we have a natural log of 2x to the power 6 minus 3x plus 2. So the derivative will give us, again, 1 over 2x to the power 6 minus 3x plus 2. Then the derivative of 2x to the power 6 minus 3x plus 2. So this will give us, again, 12x to the power 5 minus 3. And that's what we have here. And since the question, again, the reason why we have 1/3, because when we go to the original question, we see that 1/3 multiplied by natural log 2s to the power 6 minus 3s plus 7. So I'll leave the constant value, I won't touch it. Then I'll find the derivative of natural log 2x to the power 6 minus 3s plus 2. And that will give me 1 over 2x to the power 6 minus 3s plus 2 times the derivative of, again, 2s to the power 6 minus 3s plus 2, which will give us 12x to the power 5 minus 3. And that's what we have here. So finally, our answer will be 4. The reason why it's 4, because 3 can go into 12 is 4, and 3 can go into 3 is 1. So we get 4x to the power 5 minus 1 over 2x to the power 6 minus 3x plus 2. Now let's see the third question. In the third question, well, let's go to the original question. We see that we have a quotient. So we have a g at x equal to natural log 2x plus 1 over 2x plus 1. So since we are having a division here, we have to use the quotient rule. So the quotient rule says first we should find the derivative at the top times the down. I mean, the top is the numerator, derivative of the numerator times the denominator minus derivative of the denominator times the numerator, all divided by the denominator square. So here we get 1 over 2s plus 1 times 2 times 2s plus 1 minus derivative of 2s plus 1 will give us 2 times natural log 2s plus 1. Everything divided by 2s plus 1 all square. And that's what we have here. So we have again the derivative of the numerator is 1 over 2x plus 1 times 2. Then multiplied by the denominator, which is 2s plus 1. Minus the derivative at the down, which will give us only 2 times everything at the top, which will give us natural log 2s plus 1. Then all divided by the denominator square, which is 2s plus 1 all square. So we can simplify this equation. Here finally we get 2 minus 2 natural log 2s plus 1 over 2s plus 1 all square. What we did that we combine this, so we can see 2s plus 1 and 2s plus 1 will cancel each other. So we get only 2 here minus the natural log 2s plus 1 times 2. So here, using the properties of log, we know log have some few properties. Example here, if I have log base a, again log base a raised to the power x, this will give me x because the base and a, since they are the same, they will cancel, so the answer will be x. Then also if I have a to the power log base ax, also is x because a, which is the base, and the log also is base a, so they will cancel. So this is again the property of log function. Now if I have a log base a m times n, I can expand this by writing log base a m plus log base a n. Now if it's division, then it will be subtraction log. So log base a m divided by n will be log base a m minus log base a n. Then if I have log base a m to the power p, the exponent p will be in the front. So here we get p log base a m. And the natural form also is the same as the log base a form. The only thing which you know, natural log is the base is e. So we can use this property sometimes to simplify the log function before we find the derivative. So for example, here we are giving y equal to natural log s times s to the power 5 minus 2 to the power 10. If I want to, instead of using the product rule here, I'm going to expand this because I know product rule will be too long. Sum and a difference rule are almost the same amount of variables. So here we can expand this by writing y equal to natural log x plus 10 natural log s to the power 5 minus 2. And that's what we have here. Again, we use the property for the multiplication property. Here, the 10 is exponent here, so we can bring the 10 to the front using our last property. So that's what we have. Natural log x plus 10 natural log s to the power 5 minus 2. Now, if I'm finding the derivative of the top as the question was framed, derivative of this without applying the log properties, we have to use the product rule. But I think this is more shorter. After we change the product to sum, yeah, we can use the sum rule. So the derivative of this function will give me 1 over x plus 1 over x to the power 5 minus 2, 10. Then derivative in the inside will be 5x to the power 4 minus 0. And that's what we have here. So dy dx will give me, we have natural log x, so that will give me 1 over x. The reason why we have 10 here, because again, we have the exponent, the 10 here. So we can bring the 10 to the front here, and we leave it alone. Then we say this will give us a natural log, so it will be 1 over s to the power 5 minus 2 times the derivative inside, which will be give us 5s to the power 4 minus 0. Again, that's the chain rule. And that's what we have here. 5s to the power 4 multiplied by 1 over x to the power 5 minus 2 times 10. So from here, we can simplify the equation together. We get 10 times 5, which will give a 50, x to the power 4 over x to the power 5 minus 2. So we can leave the answer like this, or we can also combine if you want to. Now the b, we have this expression. So we have to use the log property, because if I'm using the quotient rule, it means I have to find the derivative at the top times the down minus derivative at the down times the top all over x squared plus 1 square. And again, we have to the power 4 here again, so that will make it a long process. So why can't we use the log properties to convert everything to a sum and differences? So first, since this is 4 here, we can bring the 4 to the front. So we get 4 times natural log cube root 3x plus 5 over x squared plus 11. Then from here, we can apply the difference. So here means we get natural log of the numerator minus natural log of the denominator, changing the division to difference. So that's what we have here now. Again, we don't want to touch the 4, so the 4 is out. And since this will be 1/3, 1/3, 1/3 also will come to the front. So 1/3 natural log 3x plus 5. Division is minus the natural log of the down, x squared plus 11. Again, the reason why we have 1/3 in the front, because cube root is exponent of 1/3. Then from here, we can find our derivative now. We know we have the natural log. So natural log of 3x plus 5 will give me 1 over 3x plus 5 times 3. So the 3 will cancel the 3 here, 1/3, so that will cancel everything. Then here we have 1 over x squared plus 11 times 2x. The derivative of x squared is 2x. And that's what we have here. The 2x is here, the x squared plus 11 Then 1/3 and the 3. The derivative of 3x plus 5 will give me 3. So we cancel the 3 out. We get 1 over 3x plus 5 minus 2x over x squared plus 11. Again, we can leave the answer like this, or we can also simplify. Here we multiply 4 by everything. So we get 4 over 3x plus 5 minus 4 times 2 is 8. So 8x over x squared plus 11. So next we have the derivative of y equal to log base ax. And we know this is one of the properties again of a log function, the change of a base formula. So for example, if I have a log base ax, is the same as writing any log or any base. So I'm using natural log. So I can say natural log x divided by natural log a. So the base a here will be in the log of the denominator. And then the value x here will be the log at the top. So again, this is one of the log function properties, change of base. Log base ax is the same as log natural log x over natural log a, or log base 10 x over log base 10 a. So if I have a question, y equal to log base 4 x cubed plus 1, they say we should find the derivative of this. If I want to, we can change the base. I can change it to 10 or natural log, or any base I want to. So here we can change it to a natural log. Here we have 4. The base is still 4x cubed plus 1. And they decided to use the natural log. Or I can use log base 10. The reason why we always use natural log or log base 10, because these two bases, it's easier to find the value of it using the calculator. So we know in the calculator, the natural log is the same as log base e. And then log base 10 also, we have the function for it in the calculator. So if I have log base 4, it's very difficult to find log base 4 in a calculator. So I can write this as a log base 10 x cubed plus 1 over log base 10 4. Or I use the natural log. In this case, we are using natural log. So we haven't yet found the derivative. Now we move to the derivative. Since this is a division, we also can apply the property to change it to minus, or we can just find the derivative here. So we know the derivative of this function, we are going to use the quotient, which if you like, we can find the derivative at the denominator times the derivative at the denominator minus the derivative of the denominator times the numerator all over denominator square. Oh, here we decided, okay, let's break it down. We have 1 over natural log 4 times natural log x cubed plus 1. Then from here, we can find the derivative. So dy dx will give me 1 over natural log 4 times, again, here we have a natural log, so it will be, because 1 over natural log 4 is a constant value. We know natural log 4 will give us a value. So we leave this, we hold down this constant value down. Then we find the derivative of the variable section, which is the x's. So this will give me 1 over x cubed plus 1 times 3x squared. So we get 1 over x cubed plus 1 times 3x squared. Then we can combine our solution to be 3x squared over x cubed plus 1 times natural log 4. We can also prove this. We know the derivative of natural log x is the same as 1 over x. Here we are using our famous formula limiting process to prove it. So dy dx is the limit as h approaches 0, fx plus h minus f at s over h. Now we are assuming that we have a natural log. So we have natural log s plus h minus natural log x over h. We combine this, we get the natural log s plus h minus its division, so divided by x all over h, using the property 4. Then here we introduce s over x here, which again is 1. And the goal is to get again and 1 over x times s over h natural log 1 plus h over x. Again, we have here s plus h over x is the same as s over x plus h over x. So s over x will give me 1 plus h over x. Then here we still have 1 over x. Then our natural log 1 plus h over x to the power s by h. Using the property v, any value in front of the natural log, we go back here as exponent. Then we bring our 1 over x, the limit h approaches 0 is natural log 1 plus h over x raised to the power s by h. Then here we're assuming to give us, we bring the natural log out, then the limit approaches 0, h approaches 0, and we have h here. So this will give us 1 over x, a natural log, as the limit a approaches 0, 1 plus a over to the power 1 over a. And we know that everything here will give us e. So dy dx will give me 1 over x natural log e, which is the same as 1 over x. Natural log e, the base is the same, so this will give me 1. Log base e will give me 1. So again, this is the proof of d dx, natural log x is 1 over 1 over x, using the limiting process. So this will be the conclusion of our short lectures on how to find the derivative of a log function. And also we discuss the log properties. So again, if you have a question, you can post it in our Blackboard, and wish everybody the best. Thank you. Bye.